Hello everyone, welcome to my channel. I'm Oscar from the Nanjing Foreign Language School. I'm very glad to meet everybody here online. Today I'm going to give an introduction about the Hohmann transfer. The space exploration has always been a fascinating subject for many people. Nowadays, with the advancements in technology, humans are able to send spacecraft and rovers to explore the planets beyond the Earth. One of the most important aspects of the exploration is the journey to the destination. In this article, I will introduce the Hohmann transfer, a technique that enables spacecraft to travel efficiently between two celestial bodies. The Hohmann transfer is an orbital maneuver that is used to transfer the spacecraft from one circular orbit to another circular orbit of different radius. It was first described by Walter Hohmann in 1925.
The Hohmann transfer consists of two main burns. The first burn is used to transfer the spacecraft from its initial circular orbit to an elliptical transfer orbit, which is known as the Hohmann ellipse. And the second burn is used to transfer the spacecraft from the transfer orbit to the final circular orbit.
This suggestion was quite surprising because at that time the artificial satellite hadn't been invited. So before we go on deeper with the Hohmann transfer, we need to know the basic elements of an orbit first.
In general, there are 6 elements of an orbit. They are the semi-major axis, eccentricity, inclination, argument of precipice, magnitude of ascending node, and the tuning anomaly. Since the last 3 will affect the state of the orbit in 3 dimensions, so I'm not going to talk about them here. The semi-major axis is the half of the larger radius which passes through the focus of the ellipse. It determines the size of the orbit. The eccentricity is the radius of the distance between two focals and the major axis. It determines the shape of the orbit. The smaller of the eccentricity of an ellipse orbit, the closer it can be seen as a circle. A circle is a special kind of ellipse. Its eccentricity is 0. The inclination shows how the orbital plane was relative to the reference plane, which usually means the angle perpendicular to the orbital plane vector, known as the equator. During the process of the Hohmann transfer, the inclination needs to be the same. The Hohmann transfer works by taking advantage of the different speeds of circular orbits at different radius. When a spacecraft is in a circular orbit, it travels at a constant speed. However, the speed changes when the spacecraft moves to an elliptical transfer orbit. This change in velocity is achieved by firing the spacecraft's engines in the direction of the motion, which increases the velocity of the spacecraft. When the spacecraft reaches the furthest point in the elliptical orbit, known as the apogee, the engines are fired again, which causes it to enter into the final circular orbit. Otherwise, the spacecraft will remain in the transfer orbit.
In addition, the direction of the acceleration is to be the tangent of the orbit due to the process of saving fuel and safety. Just let me give an example. Look at the graph. Most of us have the experiences of taking a car trip. Here the drivers wants to leave the aerodrome. If here is a ramp just at the tangent of the aerodrome, the driver can get out very easily. However, if the ramp is at the other direction of the aerodrome, the driver needs to change both the magnitude and the direction of the velocity. It is quite dangerous when a vehicle is traveling at a high speed. So does a spacecraft. Although Hohmann transfer uses the minimum amount of energy to reach a new orbit, it also takes plenty of time. For missions with time constraints, we can cut down the time by using more fuel. Instead of using the elliptical transfer orbit that just reaches the outer orbit, using an elliptical transfer orbit that extends past the outer orbit will result in a faster transfer time. This gives us the general complanar transfer. Now I'm going to show you how to calculate the change in velocity in these two transfers. Here we get an equation of the specific mechanical energy is equals to the minus mu over 2a. It is also equals to the square of the velocity over 2 minus mu over r. We can get an equation of the velocity is equals to the square root of mu over r plus the specific mechanical energy. So we can get the velocity in each period of the orbit. So the total change in velocity is the sum of the two differences in velocity. For the general component transfer, we need to know here's the concept of the flat path angle. It is the angle between the satellite's velocity and the local horizontal. For a circular orbit, the satellite's velocity is perpendicular to the position, so its flat path angle is 0. And the flat path angle can be found by using the conservation of the angular momentum. If we're assuming that the gravity is only the force that acting on the satellite, we can get an equation that is the angular momentum is equal to the relative position vector times the velocity and times the cosine of the flat path angle. And by using the trigonometry and just look at the graph which I showed here, using the cosine rule, we can calculate the square of the two changing velocity, and then we can get the total change in velocity by adding them together. Hohmann transfer is a very important technique for the space exploration. And here are some alternatives for the Hohmann transfer, like the bio-ellipse transfer and the gravity assist maneuver. This is what used by Voyager 1 and Voyager 2. Each of these techniques has its own disadvantage and advantages. For which one to use depends on a lot of factors like the time requirements, the amount of propellant available, and the specific orbital characteristic of the spacecraft. And lastly, please don't forget that the energy required to set up the engine has to be involved in the total energy costs. Otherwise, the astronauts may be in trouble in the space. Here's the end of today's video, and it's my first time to take part in the AeroTube. If you like my work, please vote me. Love you guys, and bye bye.